Welcome, everyone. My name is Vincenzo Gulisano, and I will introduce the DEBS Grand Challenge. This year, the Grand Challenge has been organized together with Daniel and Ruben from the Technical University of Munich, and Hannaneh and Dimitris from Chalmers, University of Technology. The DEBS Grand Challenge started in the year 2011 to provide a common ground and uniform evaluation criteria for a competition based at both research and industrial event-based systems. In this talk, we will cover this year's challenge, how it was evaluated, and how the awards are assigned. Let's start by looking at the challenge itself. This year, we focused on the problem of non-intrusive load monitoring. More concretely, we focused on the challenge of detecting when devices are turned on or off by only looking at the aggregated consumption of several appliances at the same time. In this challenge, we used the BLOND dataset. The acronym stands for Building Level Office Environment Dataset of Typical Electrical Appliances. And the data provided for the challenge consists of energy measurements from a smart meter. It comprises long-term high sampling rate electrical measurements from a typical office environment that can be used for electrical load monitoring or other tasks, such as occupancy detection for building management systems. Both the aggregated electrical main signal and plug level appliance measurements are provided in the dataset. For the challenge, we are using the aggregated measurements only. The appliances that are active in the dataset are mainly laptops and monitors, which induce variations into the signal. This in turn makes the event detection particularly challenging. The schema of the input tuples is defined by three attributes: the sequence ID, the voltage, and the current. The figure shows an excerpt from the dataset. In the figure, one can see the aggregated power consumption of the office and the respective measurements from the ground truth. The ground truth contains the plug level appliance measurements per office. As shown, it is possible to observe the steps in the aggregated signal that constitute the events that are to be detected in the signal. The challenge defined two queries. The first query aims at detecting devices that are turned on or off in a stream of voltage and current readings from a smart meter, resembling the aggregated energy consumption in an office building. The processing steps are described in the following. Each input tuple is first aggregated using a tuple-based window of size and advance 1000 to compute the active and the reactive power features. These are computed as shown in the slide. The resulting stream of features is then processed based on the algorithm described in the paper Sequential Clustering-Based Event Detection for Non-Intrusive Load Monitoring by parsing method. For each 1000 input tuple, the query is expected to produce a result. Such a result specifies whether an event has been detected for such a window and the sequence number of the window for which the event is detected. The second query is a variation of query 1. More concretely, this query is expected to process an input stream that can contain both late arrivals as well as missing tuples. The semantics of query 2 are equal to those of query 1. Nonetheless, participants are expected to provide a solution that is able to trade off timeliness and accuracy of results. Upon reception of an input tuple, the proposed solution can produce an output based only on the data observed so far, or decide to postpone the output after late arriving input tuples are received. In the second case, the solution can wait for possibly late arrivals to provide an output that more accurately identifies the timestamp at which an event is detected, if any. In order to differentiate between missing tuples and late arrivals, the disorder in the data we share is bound to 20,000 tuples. When it comes to the overall score, the solutions are ranked as follows. Evaluation of query 1 addresses two aspects: correctness of results and processing speed. The first is taken into account by comparing the results of a proposed solution with that of our baseline. The second aspect is captured with multiple measures: the total runtime and the latency. When it comes to query 2, we take into account the timeliness of produced results and their accuracy. Solutions that prioritize timeliness can immediately produce the result for a certain window without waiting for any potential late arrivals. This, of course, can affect the correctness of the result. When accuracy is prioritized, participants can opt for producing more precise results once they wait for possible late arrivals. But this has an impact on the timeliness metric nonetheless. Let's now move to the evaluation process. First, let's look at the evaluation platform. The participants implement their solution in their desired programming language and then package it in a Docker container. The solution makes GET requests to the evaluation platform and receives data in batches of 1000 energy measurements as a JSON object. It then runs the detection and transmits back the answer using a POST request. This Docker-based setup allows running performance evaluation in two ways. First, evaluation can be run locally. This includes only the green components. In this case, the participants use their infrastructure to test and evaluate their system's performance. Alternatively, contestants can use the full evaluation platform, which includes the orange components. Both options utilize the same evaluation container that provides the data and checks the provided answers, as shown in the green part. The extra components of the official platform provide additional functionality. The controller acts as a mediator and enables result persistence, and a web-based leaderboard ranking the submissions of all contestants. The manager is responsible for fetching the solutions, running the evaluation, and reporting the results. Finally, the scheduler is responsible for checking for new versions of the solutions and scheduling new experiments if needed. To enable automatic re-evaluation when solutions are updated, participants make their submissions available at a Docker registry, which is periodically polled by the scheduler. Input datasets include an input file for each query. Two datasets were made available for the participants. The first was a small dataset that included 500,000 measurements. The second was a large dataset that included 15 million measurements. After the deadline, the solutions were also evaluated using a third dataset of 20 million measurements that was not given to the participants. There were 9 solutions submitted from a total of 5 teams. There was an interesting variation in the solution strategies, with some solutions trying to balance performance in all metrics and others focusing on only some of them. When examining the execution of the largest dataset, the total runtime ranged from 31 to 50 minutes. The latency ranged from 75 milliseconds to 62 seconds. The timeliness ranged from 0 to 20,000, and the accuracy ranged from 8 to 54. Now let's move to the last part of this presentation. This year we had 21 teams registered in our submission platform, and we finally have 5 finalists presenting today. When it comes to the awards, this year too, we have the Grand Challenge Award for the best performing solution, and the award is of $1,000 this year too, and the audience award. In this case, the voting will be done via Slack. And without further ado, let's now move to the participants' presentations.